Hello and welcome to our talk integrating your big data system with graph data science and Apache Arrow. We will show you in this talk how you can easily integrate any data system, any data processing system that you have with the Neo4j GDS library. With me is my colleague Sören. My name is Max Kiesling. We are both software engineers at the graph data science team at Neo4j. To get right in, for the uninitiated, what is GDS? The Neo4j Graph Data Science Library, or short GDS, is a Neo4j product that helps you analyze and understand your graph data at scale. It is a plugin to the Neo4j database that allows you to create in-memory projections of your graph data, either directly from your Neo4j database or, as we'll demonstrate in this talk, from many other data sources. The in-memory projection of GDS is basically an optimized computation representation that allows us to compute graph algorithms on hundreds of millions of nodes and billions of relationships and even beyond that. GDS itself ships with a large selection of both classical algorithms like PageRank, community detection algorithms, pathfinding algorithms, and many more, as well as more advanced algorithms like for machine learning like node and path embeddings. The computation results that are computed by the GDS library, they can either be consumed as streams and be sent to any other processing system to be further processed, or they can be persisted to the Neo4j database itself. The other framework that we are going to be relying on in our talk is Apache Arrow. Apache Arrow, at its core, is a specification of columnar in-memory formats that are both language independent and designed and optimized for analytical workloads. Apache Arrow, defines value types like strings, integers, floating point values, and lists thereof, and many more, and their memory layout, and specifies how to represent these values as vectors. This specification then allows to share data in memory between multiple processes without having to copy or reinterpret the data. Today, there exist many implementations of Apache Arrow for all the major programming languages like C++, Java, Python, and Rust. As an extension to Arrow, we have Arrow Flight. And Arrow Flight defines a high-performance RPC framework based on gRPC and HTTP2, which allows to exchange the Arrow data between services that are not co-located on the same machine. In this talk, we will be heavily relying on Arrow Flight, and we will most likely just call it Arrow from here on. And when we talk about the data that we're sending, the Arrow data that we're sending, we'll talk about vectors. So in this talk, we will mainly focus on GDS graph projections and how we can actually create GDS graph projections from data that lives anywhere but Neo4j. Today, there already exists a couple of methods that allow you to create Neo4j, create GDS in-memory projections. Most notably, of course, we can project GDS in-memory graphs from any Neo4j database. That is possible via either native or Cypher projections. You can use the Graph Data Science Python client that comes or that works nicely with GDS, which is able to use pandas data frames to project those into GDS in-memory graphs. And you can also export and import CSV files from and into GDS. And if you have no graph data at all, but want to play around with GDS, or you just want to try something, then GDS has a built-in capability of creating random graphs based on a large set of different characteristics. So what about big data, though?
Yes, exactly. What about big data? So when we look at the diagram that Max has just shown, there is no direct way of projecting graphs by reading data from Spark or Flink or whatever. We look at the next slide. So usually, and also Hannah Fry this today underlined this. Usually what companies do nowadays is they store large amounts of data in some warehouses, usually in cloud storages nowadays, in order to analyze this data later to get insights into their business. And they do this usually by processing this data using some distributed processing systems like Spark or Flink, for example. Yeah, but in the end now, what we want to achieve is that we want to get this data out of the storage and project an in-memory graph, because we think that GDS is a great tool for exactly that analysis that those companies want to achieve. But how do we get there? So today there is actually a way to achieve this by slight detours. So we can use one of the sources that Max explained are provided today. For example, Neo4j or the Python client, and we can project a graph from there by having another so-called, or we call it now, import layer. For example, in the case of Neo4j, we can basically pull all the data out of the workers and store them in the database and then project a graph out of that. Or in the case for Python, we can have another machine and get the data and then forward it to some Neo4j instance that hosts the GDS and project a graph there. And if you're seeking for having your data also in Neo4j in order to have a graph database and the graph that you want to process further, that's totally fine. And then this is probably the perfectly sane way to do all of this. But on the other hand, if you're just looking for projecting an in-memory graph in order to read from your processing layer to get some analysis done, then maybe that's a slight detour. And as we can see here, if we don't need this import layer, we might have other problems as well, because in the case of a Python client, we might need another machine where we collect all the data from the processing layer, and then we need to forward the data to the analytics layer, as called here. But this might cause the machine to fall over because we are collecting huge amounts of data on it. Maybe that machine isn't meant to do or to process this amount of data. So at best, all of this is one hop too much for the data to travel, and at worst, your machine could fall over. So yeah, what would an ideal world look like? So in an ideal world, like I said, we would directly forward the data from the workers to the analytics layer to GDS and project the graph based on the data that the workers processed. And in order to do this, now Arrow comes into play. Next slide, please. So if we zoom in a bit into what the workers do in this processing layer. So usually you want to transform your data in order to work with it in the end. So that could mean that you're doing mapping, transforms, filtering, projections, whatever. In order to now achieve to directly project a graph, we mainly just need to spawn an Arrow client on each of these workers in order to send all of this processed data to the GDS server. And that GDS server will host an Arrow server that can collect all the incoming streams in parallel and then project a graph out of it. And in fact, the graph projection in GDS is always, or was, parallel from the get-go. So this plays very nice with the capabilities of GDS. And the advantages, so far we didn't specify which distributed system we are talking about. And the good thing is, it doesn't really matter because the Arrow clients you can implement in many different languages. A few of these are shown here. So there's a good chance that with the system you are using, there will be one language supported where you can implement an Arrow client on a worker. So the only thing that's missing now in order to send those data over to the GDS machine is the way that our Arrow server expects the data to look like and the protocol we use to communicate with that server. And this is done by the Arrow graph projection protocol. So in order to understand how this protocol works in theory, we need to understand how a projection in GDS works. And the projection in GDS is a two-phase computation, basically. That means we at first need to send all the nodes data because GDS projections rely on consecutive ID space. So we are remapping IDs, which helps us later to get better compression and has other computational benefits. So once that is done, we can start sending the relationships that depend on the node data being sent. So this means that our Arrow server is basically a big state machine that we need to progress with the Arrow protocol. So let's have a deeper look at what the protocol looks like. So you can see in the legend on the right, so this diagram will show the connection between the client and GDS, and in the diagram, the legend to the right, we can see two things we need here, and these are both arrow terms. So one thing we need is an action. An action is a message that the client sends, which is basically just some arbitrary JSON, which is, like the name says, just an action. So the server reads it, and it will either reconfigure itself or set itself into a state that you would like, and usually that's a very lightweight operation. So and the put stream, on the other hand, is where you actually send the data then. So yeah, there you will send arbitrary streams of data that you define to the server, and the server will handle those streams. So when we look at the first step of the protocol, we will start by sending an action, and that action is create graph, and we pass along a graph name, which has two purposes. One purpose is that the server on the other side will spawn a process that is referenced by exactly that name. And the other thing is that in the end, when we project the graph will have exactly that name, or will be registered with that name that we passed on. And once we did that and it was successful, we will get back a simple ACK message that the server did this job successful. Also, what happens under the hood is that the server sets itself into a state that it accepts or expects that node data will be sent next. And that's the next step. So from the client, we are now sending node data as a stream to the server. And we will get as an ACK message back the number of nodes that the server actually received and stored in the projection. The next step will be to signal the server that our node loading is done. And this might seem a bit ambiguous, but we actually need to signal the server explicitly that it is done, because as we saw earlier in the diagram or in the architecture, that we have actually parallel workers that each spawn a client that can all send in parallel to the server. So the server has no idea about how many clients are out there sending data, or how many batches. So we need to explicitly call from one source that the node loading is done. And once that is done, we will get a message back with the total number of imported nodes. And also this will progress the state machine to set the server into expecting relationship data now, which will happen next. So next, the client is expected to send relationship data to the server. And this is basically the same as with nodes, just with differently formatted data. We will get as an ACK message the number of relationships in each batch. And last but not least, we are signaling the server for the same reason as before, that we are done with the relationship loading, and the server will respond with the number of relationships imported. And also under the hood, the server will finish up the projection and store it in the graph catalog. So from then on, you can use it for your regular GDS workloads. All right, let's have a look at the demo we're about to show you. So we will be implementing basically what we see on the right. So we have some distributed system, and in our case, this will be a Spark cluster with 4 workers and hosted on GCP. And we will send projection data, or data we want to project in the memory graph from, to a GDS instance. And that GDS instance will be an RIDS professional. And the Arrow client we will be implementing in Python and submitting the job via Python. The data we're about to send is a data set. It's a LDBC data set. It's usually a benchmarking data set. We're using scale factor 1000, so that's fairly large. But we are projecting only a subgraph of that for demonstration purposes, only using the person knows person subgraph. That's still somewhat large, so we are talking about, I think, 3 million nodes and about 200 million relationships we're going to send. And now off to Max.
All right. I'll switch to our Jupyter notebook here that we've prepared. That Jupyter notebook is connected to our Spark cluster in GCP. Yeah, we'll start off with the imports here. That's not too important. And as the next step, we can initialize our Spark session. The only interesting thing, here is that we are setting this Arrow PySpark enabled option to true. That means that Spark in this session will actually use Apache Arrow as its transport and data layer. That will be beneficial for us later and actually makes for a really nice integration between Spark and the whole Arrow ecosystem, and specifically the GDS Arrow Flight endpoint that we will be connecting to. So we can go ahead and create our Spark session here, and nothing happens yet. We also need to load some connection info. I don't want to show you the connection details of our GDS instance and where we connect to. So I've hidden that in the file, but there's nothing special going on here. It's just the Neo4j username, Neo4j password, and the URL of the Neo4j instance that's hidden in that file. And then we can already dive right into the interesting parts of the implementation. We'll start with a function that allows us to, on demand, create a flight client. The flight client is basically the client to the Apache Flight Server that we want to talk to. We are using the Python variant here. We previously imported PyArrow. That comes bundled with this flight client. From our connection info here, we will just collect all the necessary information that we need, and then assemble our connection URL, and then start the client with connecting to the server. As a very first step, what we need to do then is we need to authenticate. And authentication here is done with the very same credentials that you would normally use when you connect to your Neo4j instance via Bolt or via the Neo4j browser, for example. So it's the exact same.
Sorry, Max, there was a request to increase the font size a little bit.
Sure.
That's possible. Thank you.
Sorry for that. So we connect to our server, we authenticate ourselves with username and password, and what we get back here is a token. The token we can later use to not have to authenticate ourselves again, so we don't have to send username and password with every request. The reason why we are creating a flight client in a function and not as a one-off thing here is because we actually are going to send, or we are going to talk to the GDS flight server from different machines. We are both going to talk to the flight server from the driver machine that is actually driving the PySpark program here. And that we will do in order to send the actions, which are the coordination points between our state machine steps. And then we will talk to the flight server from our worker machines in order to send actual data. And that's why we've hidden the creation of the flight client behind this function, because we can serialize then this function and send it to the workers. Next, we will define another helper function that will allow us to actually send actions. Sören already talked about the different actions that we need to send to the server in order to communicate the transitions between the different states of the state machine that make up the input process. This function takes three parameters, just the connection info again to create a client. It takes the action type, which is just a string, and it takes some metadata that the action may or may not need. That's just a dict that we will later encode as JSON and put into the action payload. And all the rest of the code in this function is straightforward. We just use our client to call the doAction function. We create a new action with the action type. We encode our dictionary as JSON, and then send it off to the flight server, and then we get some information back. That's also JSON. We decode that information and just print it for demonstration purposes here. With that set up, we can actually start our import process. So we will now use our send action function to actually send the create graph action that will initialize our import process. And we need to also specify two mandatory parameters here. We once have the name. The name is acts as both the identifier for our import process, so we can later refer to it when we want to actually send data or transition the state, because there could, in theory, be multiple concurrent import processes. And then we also need the database name. That's just for internal reasons, and because how the graph will later be stored in the GDS graph catalog. So if we actually execute this, it doesn't work, of course, because it's a demo. Why did I not do that? Yeah, now it worked. Right, so if everything goes right, then the server will answer with the simple acknowledgement message, basically saying, okay, I've started a import process and I will reference, or it will be referenceable from now on with the name G here. Now it's time to actually send data to the server. And for that, we need to specify another function that we call doPut, and basically an inner function that we call doPut partition. The doPut method accepts a single Spark data frame, as well as some metadata that might be needed alongside the actual data that we want to send to the server, and again, the connection info. And here comes a very interesting point, which is the map in arrow function that is provided on the PySpark data frames. So remember before when we initialized the Spark session, we enabled Arrow as the transport and data layer for the Spark session. And that actually allows us now to actually access these raw Arrow data batches from our workers. By calling this function and providing another lambda, the inner function here, we can actually say, now for each raw Arrow record batch that lives on any of the workers, execute this function. So each of the workers that we have on our cluster will execute this function. The function receives a batch, an iterable of record batches. So record batches are basically batches of Arrow vectors. And it's multiple batches because each worker in our Spark cluster could, in theory, be processing multiple, basically data frame partitions. So we get potentially multiple of these batches per worker. But this function now is effectively going to be executed on the worker. So again, nothing special in the beginning. We create our client, and then we need to extract the first batch from our batches iterable. Because in order to initialize the put process, the server needs to know what the layout of the data is that we are going to send, and we can actually just infer that by looking at the data. So we will get the first batch, access its schema method, and with that we'll create our writer that lets us write actual Arrow vectors and batches to the server, and we'll do that now. We will write the first batch and then all the other batches, and once we're done, we close the writer, and by then we're good. We need to return an empty list because it's a map function, so we need to return something, but effectively we will be consuming the data frame at this point. So now it's probably a good time to quickly talk about the data frame format. I'm going to switch back to the presentation real quick. So we have an expected format for both the nodes and the relationships. For nodes, we have one mandatory column. It's called node ID, which is a globally unique integer that basically acts as the identifier for the node. And then we have a reserved keyword, which is labels, which allows to specify a string or multiple strings or a dictionary encoded list of strings to specify this node with this ID has labels A and B, and all the other columns in the data frame, they will be interpreted as node properties. The format is very similar for relationships. We have source node ID and target node ID this time, which reference a previously loaded source node or target node. Then we have a relationship type, and every other column in the data frame will be interpreted as properties for the relationship. our data in this use case or in this example lives in HDFS as Parquet files, and so we can go ahead and since we want to load person knows person, we need to start with the person nodes. So we'll load those person nodes from the HDFS. We will format the data in the right format. So it's got an ID column. We need to rename that to node ID, and we need to project the label here in this for this example. So we can go ahead, and then we should end up with a person data frame, and now we can transfer that person data frame to GDS, to the GDS server by running the do push function with our person data frame. That's it. That's already done. Now we've loaded all our nodes. In theory, if we had more nodes to load, we could call this do put function multiple times. Here we only have one data frame. So we'll send our node load done action, and we'll receive that we have now loaded 3.2 million nodes. And now we can do the same for relationships. Again, it lives in a Parquet file. Same spiel. Again, we have source node ID, target node ID. We create a label from a literal because we know all those relationships will have the same label. And we load the data frame and then transfer that over to GDS. That's going to take a while longer because that's now over 10 times the amount of data that we're going to send. It's about, I think, 200 million relationships. It's not really 10 times the amount of data, but it's considerably more. It's still it's going to take about 30 seconds in all our other tests. So we're almost done here. And we're done. So with that out of the way, we can actually run our final action. We say relationship load done. We run that. And now there's some processing happening in GDS. It basically finalizes the in-memory projection, puts it into the catalog, and now tells us I've loaded roughly 202 million relationships. And we can now actually, sorry, I need to find my tab. It's gone. Here it is. We can now switch to, this is Neo4j workspace connected to our GDS instance, and now we can say call gds.graph.list, and the graph is called G, and need to spell it correctly. And then you can see now we have loaded a graph with 3.2 million nodes and 202 million relationships with a total resident size of roughly 2.2 gigabyte. And now you could go ahead and do your general processing with GDS. There's also a way to actually retrieve Spark from retrieve data from GDS into Spark, but we're running out of time, so I'll skip those slides. There will be examples in the notebook that we'll share later. So if you're interested in that, look into that, and over to Sören.
Right, so let's talk about some takeaways and what we hopefully learned in this talk. So at first, I hope we learned that the integration between arbitrary big data, distributed processing systems, and GDS is fairly simple and can be achieved with Apache Arrow and by implementing the graph projection protocol that hopefully also isn't too complicated. What we also saw is that Arrow, on the other hand, has excellent integration with many data science frameworks. Like for Spark now, we used Apache Spark, which did a lot of convenience things that makes it very easy to work with it. And Pandas, for example, they recently implemented an option to change their backend to use Arrow vectors and the tables underneath. So there's also no transformation of data necessary if you use pandas. And last but not least, we have seen that Arrow Flight allows performant data transfer, in our case, by not only reducing an unnecessary hop between the data and the in-memory graph, but also by sending all that data in parallel to our server. And what I forgot to say is, in case you wonder if where the Arrow server lives or if it's enabled or not, usually you can just enable it by flipping a config in the Neo4j settings to enable that server. But if you're on RADS, such an Arrow server is always enabled, so you can dive right in. And yeah, thanks for your attention. Here are a bunch of links. One of these I shared already in the chat, which is the demo code. There's also documentation for the protocol we have just shown on GDS, and also link to the Arrow documentation, which might come in handy. Yeah, otherwise, thank you. And we can, I guess, answer a few questions if there are some.
There was one question asking if this approach could be used to ETL data. And if you say to Neo4j graphs, so you can of course do ETL in Spark and do with your data then whatever you need to do in Spark, and then you can send it to GDS. There is also that's not an option we do promote a lot, but there is an option to actually, instead of loading the data into a GDS in-memory graph, you can also load the data into a new Neo4j database that actually works. Instead of running the first action as create graph, it's then create database, and that will, using the parallel batch importer, import your data into a new Neo4j graph database. If your Neo4j installation allows that, that's not possible on Neo4j Aura at the moment because it doesn't support multi-DB. All right. If there aren't any other questions, then thanks for listening and enjoy notes.
Yeah,
Thank you.
thank you very much. See ya.